Hello students, in this video we'll find a formula for the inverse of an injective holomorphic function on a domain. So let's be given f mapping omega into c, an injective holomorphic function. These injective holomorphic functions are sometimes called univalent functions, right? So you're going to see the word univalent in a lot of textbooks, called univalent. Okay, that's what univalent holomorphic functions are. Then we know from a previous work, we know that f prime of z is zero free in omega, is zero free in omega. We proved this in the previous video, right? Okay. So now what I want to do is the following. So we also know from the open mapping theorem that f maps open sets to open sets. That for any open disk dPr with its closure containing omega that f of dPr is an open set. Then f of dPr that's open is an open subset of the image, right? Okay, and so that's the situation we're going to consider, right? So here's our set omega, right? There's our set omega. Here's a point P, and then this disk of radius r is contained in its closure from this configuration is also contained in omega, right? And it's going to map this disk over here, maps P, into just some other open subset. Let's do it with some dotted lines to make sure that we know it's open, right? Some other open subset over here. This is going to be f of dPr, like that. It's open, okay? Excellent. All right, and so now what I'm going to do is the following. I'm going to pick a w over here. So pick w. Okay? So w is in the image, so w is in f of dPr, right? Okay? Excellent. So now what we're going to do, and that means that there has to be a unique. This implies there exists a unique. There is a unique z tilde in dPr such that f of z tilde is equal to w. Okay, this is an important feature over here. And so now what I'm going to do is the following. So now, let's consider 1 over 2 pi I, the integral over this circle over here. So what's that circle going to be? It's going to be points z minus p equals r. So of course, z minus p equals r is that set over there. That's z minus p equals r. Okay, that's that circle over there. And of course, where does our z tilde reside? Our z tilde is somewhere over here, right? So that's where our z tilde is, right? Somewhere over there. And there's only one point by the fact that it's an injective function, right? And so of course, this is the only z tilde that works. This is the only z tilde that works. Great. Of what? Of z times f prime of z over f of z minus w dz. I'm going to evaluate this integral over here, okay? So of course I can do it two ways. The first way is that I can just use the residue theorem if I want to, right? Because of course, where is this function singular? This function is singular at z tilde because z tilde will output w, right? So this is the integrand. So this is going to be by the residue theorem. or use the argument principle, either one works. by the residue theorem, this is equal to the residue of z f prime of z over f of z minus w at what point? At the point z tilde, okay? And of course, since f prime can't be 0, this is a simple pull, right? So z tilde, note, z tilde is a simple pull. Okay, so that allows me to conclude that this is going to be what? This is going to be the derivative, so it's going to be this function over here over the derivative of the denominator, which is not 0. The derivative of the denominator is what? 0 free, so that's fine. It's going to be what? It's going to be, I'm going to plug in z tilde, so I'm going to have a z tilde f prime of z tilde over what? Over f prime of z tilde, which is just z tilde, right? But what is z tilde? Z tilde is equal to what? Z tilde is equal to f inverse of w. This is f inverse of w. So what's our conclusion? Our conclusion, all these things are the same, so I'm just going to write down what this is equal to. So f inverse of w is 1 over 2 pi I, the integral over z minus p equals r, and then z f of z over f of z minus w dz, and there's a prime up here, right? In other words, this is a formula for the inverse function of a holomorphic function in a region where the function is univalent. So this formulation over here is very, very useful because what it does is it represents the inverse function as a sort of a Cauchy integral operator, right? So in other words, what I have now is I have a way of representing inversion, complex inversion of univalent functions by a formula like this. Very, very useful because what this allows me to do now is this allows me to actually try to write down operator theoretic versions of inverse functions if I'm trying to do pre-images or pullbacks, and this formula will help us out a tremendous amount when we start studying conformal mappings, right? Conformal mappings are the mappings which are, have to be locally one-to-one. In some region it has to be more broadly univalent, right? And so in the study of univalent functions and in the theory of complex variables, this sort of representation is extremely useful. Integral representations give us access to all sorts of properties of the function that's being described by the integral representation. But the underlying assumption here, of course, I'm using a lot of properties over here. I'm using the fact that an injective function and an injective holomorphic function or a univalent function, univalent holomorphic function, has a zero-free derivative, right? The zero-free derivative guarantees that this pole over here is simple. I need to use the open mapping theorem to make sure I can actually make sure that this thing is open so that I don't hit any points on the boundary and get out of that circle range, right? So in other words, I don't want a point on the boundary where I can't actually integrate over there. So in other words, that may sound like a subtle point, but I want to make sure that that z tilde is not on the boundary, right? So this has to be an open set, right? That's where the open mapping theorem comes in. So that's a very powerful theorem, right? I'm using two powerful theorems to get access to this formulation, this integral formulation of the inverse of a univalent function, which is a very, very powerful tool. So it sort of encapsulates a lot of the main ideas we've been studying in terms of the open mapping theorem, in terms of Roche's theorem, Roche's theorem, as well as the argument principle. All these things play an essential role in this formulation. Thank you very much.